So now this video discusses about what we call as the gravitational potential energy. Just have to say potential energy, and I'll also be able to look and understand about the concept of the actually conservation of the mechanical energy. So what is the gravitational potential energy? As the name itself suggests, a gravitational potential energy, it is the energy due to the gravitational force, or it is the energy of a height, or the energy due to the position of an object. That is what we call as the gravitational potential energy. You just have to say it as the potential energy. Let's say we have an object. Let's say this is the object of, let's say, mass m, and the object is being, let's say, moved upwards. And let's say this is its initial position, or call it as the position of h1. And let's say this is somewhere up, and let's say this is the position 2. Let's say that is the case. And now this object being moved up, it has gained the height. And what is the actual height gained? The height gained, it is given as the height h. You should have that one. So we understand that the force should be the work done is given as the force times distance in the axis of motion. But now what if the force, it is the force due to the gravitation force? Now the force, according to the Newton's second law of motion, we'll have it as the mg times the distance. Now since we are talking about the vertical motion, then the distance will be given as the height. So for this case, the work done due to the gravitation force will be given as the mgh. Now the work done due to the gravitation force carries another name, which is given as the gravitational potential energy, which is given as u is equal to mass times acceleration due to the gravity times the height of the object. So this is the formula for the gravitational potential energy. And the gravitational potential energy increases with the height. If the height increases, if the object is gaining height, it means the gravitational potential energy also increases. If the object is losing height, it means the gravitational potential energy will also actually decrease as well. So keep that in mind. And let's say we have the object of mass, let's say 5 kgs. So what is the value of the gravitational potential energy at, let's say, the height given as 5 meters, and also the height given as, let's say, 50 meters, and also the height given as, let's say, 20 meters, and also the height given as, let's say, should be about 15 meters. So what did you see? Now for the first case, we are looking for the gravitational potential energy at the height of 5 meters. At the height of 5 meters, that is given as the mgh. And what is the mass? We have it as 5. But actually, by the way, mass has to be in kgs. And acceleration due to the gravity is given as that in terms of the height, which is 5 meters. And at the end of the day, we should have it in joules, so we can be able to have the gravitational potential energy in that way. Likewise, we should also have the height associated with the following gravitational potential energies, and therefore the object of the mass given as 60 kgs. We should have the height corresponding to the following gravitational potential energies. Let's say 200 joules, we should have the height corresponding to that. And we should have, let's say, 512 joules, and let's say we have the gravitational potential energy of 15,000 joules. We should have their corresponding heights if that is the case. So that's how we calculate the gravitational potential energy in that way. Now let's be talking about the conservative forces as well as the non-conservative forces. So conservative forces, these are the forces that do not change. Conservative forces, these are the forces that remains constant or do not change. So they remains constant. So they remains constant. We call them as the conservative forces. You know, at each and every point, these forces remains the same. And the good example of the conservative forces, we have what we call as the gravitation force. And also we have what we call as the electrostatic force. We have what we call as the electrostatic force. So gravitation force, it is the force due to the gravity, which is always point downwards. And electrostatic force, it is the force of electric due to the stationary charges. All these are the examples of the conservative forces. You just have to bear in mind. And we also have what we call them as non-conservative forces. These are the forces that, you know, keeps on changing according to the conditions. We have the likes of friction force. They are part of the non-conservative forces. We have the spring forces, also that the non-conservative forces. You know, forces that might change time at a time. So keep that in mind. And now that we have talked about the conservative and the non-conservative forces, let's talk about what we call as the mechanical energy. So mechanical energy, this is the energy due to a motion of the object. In other words, it is the energy associated with the position of an object and the speed in which it is moving with. Therefore, mechanical energy, it is given as the kinetic energy plus the potential energy. These are actually components of energy. They are the ones that made up of the mechanical energy. So whenever the kinetic energy increases, it means the mechanical energy of a system also increases. And whenever the potential energy increases, it means the mechanical energy also increases. And likewise, you just have to get that on up. So mechanical energy, it is the energy of a motion associated with the potential energy as well as the kinetic energy. So mechanical energy, it is the energy associated with the mechanical, actually potential energy as well as the kinetic energy. That's what we call as the mechanical energy. Now, on the part of the conservative forces, mechanical energy remains constant. On the part of the actually conservative forces, mechanical energy remains constant. Mechanical energy remains constant because we assume that there is no loss of energy in any other means. Energy from the kinetic energy is converted to potential energy. Likewise, from the potential energy converted to kinetic energy. That is, the mechanical energy being constant for the actually conservative forces. While in non-conservative forces, mechanical energy actually keeps on changing. It is not conserved. At one point in time, it will be something else. And at other point in time, it will be something else because there is a loss of energy in cause of the system. So for the actually conservative forces, mechanical energy is constant, and while for the non-conservative forces, mechanical energy actually do not remain a constant. So let us see how we can mathematically express about the energy, mechanical energy conservation for the actually conservative forces. So bear in mind that according to the principles behind the work energy theorem, you know, the total work done on the system is given as the force applied times the displacement covered. And this is the same as the change in the kinetic energy. And you should have to understand this from the perspective of the work energy theorem, which states that the total actual work done is the same as the change in the kinetic energy. So keep that in mind. And what if the work done, it is the work done by the conservative forces, specifically that is the potential energy. So the work done by the conservative forces will be given as the WC. That corresponds to the work done by the conservative forces, and which is the same as F times AC, which is equal to the change in the potential and actually change in the kinetic energy, which is the same as final kinetic energy minus the initial kinetic energy. We'll have that understood. So you should have to bear in mind that the work done by the conservative forces, is specifically that of the actual gravitation force, is given as this. So in all cases, a work done by the conservative forces is given as the negative, should be negative change in actually a negative change in the actually a potential energy. And this is true for all actually conservative forces, in the sense that, let's say if we have an object being raised up, so from the fact that the object is being raised up, the object is gaining height. For that case, this is initial position and this is the final position. Now for this case, the final position is larger than the initial position. Therefore, the change in the positions will be positive, and that corresponds to the increase in the actual potential energy. But now the fact that the object is moving against the direction of the gravitation force, it means there is a negative work being done by the conservative forces. And also in the same case, if the object is falling down, this is the initial position and this is the final position. I can call it as, let's say, H2. Now since the object is moving downwards, it is moving in the direction of the gravitation force, and of which we expect that the work done by the gravitation force on the object is given as the positive. But now from the fact that the object is moving from up to down, you should have to understand that the final position is less than the initial position. Hence, the change in these positions corresponds to the negative. Hence, also have the negative. So in all cases, in all cases for the conservative forces, that is the gravitation force, the work done by the gravitation force on the object is always the negative potential energy. In all cases, either the object is moving up or the object is moving downwards. Gravitation, actually work done by the conservative force, which is the gravitation force, is given as the negative. So that simply means that is the same as having it as the work done by the conservative force is equal to the negative. Now we'll have the final actually a potential energy minus the initial potential energy. Of course, this is the same as having it as final kinetic energy minus the initial kinetic energy. So that's how you start to understand that and for this case. And there is something that I should also have to express about actually before we come for this. But let me just have to say something on that. You should have to understand that if this is the work done by the conservative forces and being given as this, you should also bear in mind that this is also the same as, let me just have to give you this, then you should have to appreciate. The work done by the conservative forces is given as the initial actually potential energy minus the final potential energy. Should be that. But this is also the same as having it as the negative, negative times the negative initial potential energy plus that of the final potential energy. From the fact that if we have A minus B, this is the same as the negative A plus B. It is the same as that. Therefore, this is what it means. And on the same case, it means we have the negative, actually negative, times the final potential energy minus the initial potential energy. Should be this analysis. So what it means is that, the work done by the conservative forces is specifically potential gravitation force will be given as the negative times the change in potential energy as it is being depicted there. So that's why I was saying, in all cases, conservative forces, actually their work done corresponds to the negative change in the potential energy. So that's what it entails there. So if this is okay, let me just have to emphasize much on this as well. Keep in mind that, you know, the work done by the conservative forces is given as this. And also this is the same as having it as the negative should be changed in what we call as the potential energy. It is the same as that. And let's use this concept to have the energy conservation for the conservative forces. So we know that the WC is given as Fs and is equal Kf minus Ki. That is the change in the kinetic energy. If WC is also equal to that one, it means you know, WC will be equal to the change in the kinetic energy, which is the same as we have it as initial kinetic energy should be initial potential energy minus the final potential energy, which is equal to, you know, final kinetic energy minus the initial kinetic energy. We'll have this one as that. If that is the case, let's bring the initials together and the finals together. We'll have it as the initial potential energy plus the initial kinetic energy is equal to, you know, final kinetic energy plus the final potential energy. So this is what we call as the this is what we call as the law of conservation of mechanical energy, and this is only for the conservative forces, which means initial mechanical energy is the same as the final mechanical energy, and this is only true for the actually conservative forces. So that's how you start to understand that one. So in all cases, you start to get that for the conservative forces, initial actually mechanic energy, it is the same as the final mechanic energy. That is initial mechanic energy, it is the same as the final mechanic energy, you know, which corresponds to the sum of initial potential energy plus the initial kinetic energy, which is equal to final potential energy plus the final kinetic energy. We have that one, which corresponds to have it as mgh. This is the first position hi, and plus we have half mu square, that is the initial velocity of the object, which is equal to mg actually h2. Let me just have use mg actually hf, that is the final position, plus half mv square, that is the final velocity of the object. So this is what we call as the law of conservation of the mechanical energy, and basically only for the conservative forces. So keep that in mind. So let's say we have this typical question. Let's say we have a 0.104 kg, that is the mass of the object, 0.140 kgs, and thrown. We have the mass, which is given as that, and the object is thrown up with the initial velocity, that is the initial velocity. We have it as that 5 meters per second. And now the question continues to find the total energy of the ball, the maximum height of the ball, and the kinetic energy and the velocity of the ball at 30 meters. Now for this case, as the object has been thrown upwards, it will reach the point where it will never be continue going. That point, it means the final velocity will be given as well. So it should be that. So the first part of the question says that we should have the total energy of the ball. That is now by using the law, actually that is now by using what we call as the work energy theorem, which is now to be said to be, you know, that of the total work done on the object is given as should be that of the change in the kinetic energy, and the total work done will be given as final kinetic energy minus the initial kinetic energy. What is the final kinetic energy? We have it as, it should be half mv square minus half mu square. That's what it means there. And that we should have it as being given as, now in this case, in this case the final velocity will be given as L. What will have it negative half, mass is 0.14, L times velocity, which is 35 to the power 2, and the energy will be given as negative at 5.8 joules. So this is what equates as the total actual energy of the ball, and of which total energy of the ball will now be given as the positive 85.8 joules. So this is what equates as the total energy of the ball. So which means the object upon being thrown actually up. So which means upon the object being thrown straight up, its actually initial kinetic energy has been converted to the potential energy at some height. So this is what equates as the actually a total energy associated with the object. So keep that in mind, 85.8 joules. Now the question actually B says find the maximum height of the ball. So in this case we can have to use the law of conservation of the actually mechanical energy, in the sense that actually from where the object has been thrown, its initial height is given as L, and we have the final height, that is what we don't know, but we should have to deduce that one. We should have it that. So according to the law of the conservation of the mechanical energy, initial mechanical energy plus the initial kinetic energy will be equal to that of, should be the final potential energy plus the final kinetic energy. We should have that. And what is the initial potential energy? Since the initial position is L, it means we'll have it as L, and plus what is the initial kinetic energy? We already have it as half mu square, and which is equal to what is the final kinetic energy? Should be a potential energy, we'll have it as mgh2, and what is the final kinetic energy? We'll have it as our, since the object is now at the maximum position where the velocity is L, so have it as L. Then I will be able to have the height, since we already have, what is that one, which is 85.8 is equal to mgh2. We just have to solve for the height like that. So that's how you start to understand that one as well in that case. And how about the question? Should be a question, a part C. We should have the kinetic energy and the velocity of the ball at 30 meters. Should be that. So using the same principle of the conservation of the mechanical energy, initial mechanical energy should be initial potential energy plus the initial kinetic energy is equal to final potential energy plus the final kinetic energy, like that. And since the object is from the ground, it should be from the ground level where the initial position is L, we have it as, we should have it as mgh1, as we already put it forward, and mghi plus half mu square is equal to mgh2 plus half mv square, like that. So we already know that this is L, we'll have it as L, and plus we have, what is this? So that is half mass. We already have that one, that we just have to calculate. We already have 85.8, which is equal to, now we are looking for the final kinetic energy, which is this. And since we have the actually H2, which is 30, for this case the H2 is given as 30, so we have it as mg times 30 and plus the final kinetic energy. So with this we'll be able to have the final kinetic energy, which is given as 85.5.8 minus whatever you have here, and from there the other part says we should have the velocity at the final kinetic energy. That will be given as kf will be equal to half mv square. You'll be able to have the final kinetic energy there.